Right, grade 12s, welcome back. Let's continue with our electrical circuit series. Okay, so today we look at probably the last part of the electrical circuit, in which we look at the batteries and internal resistance. Batteries and internal resistance. So you look at a battery, what do you see? You see a source of electricity or electrical power. That's what you see. You see a source. But remember now, a battery also is made up of internal components, mostly the wires that are internal to the battery. Those are also potential consumers of the same energy that it produces. All right, so this makes interesting. Let's look at it. Okay, so as I said, batteries are made from materials which have resistance. Okay, so there's therefore not just sources but potential of potential difference, but they also possess internal resistance. The internal resistance consumes some of the energy that is produced. Okay, so if the total potential difference source is referred to as the electromotive force. So what are we saying? We're simply saying there are two here scenarios that we need to look at. The battery is going to produce energy. Okay, so it's a source of energy, so it's going to produce the energy. But when it produces the energy, there is going to be internal consumption of the same energy, but not all. A small portion is going to be consumed internally because of the internal resistance. So as the charge is moving out of the battery, it needs energy to overcome the resistance of the internal components of the battery. That resistance, we are going to call it R. So it's going to be represented here by the small letter R. Okay, and the total voltage that is going to be produced, that is known as the electromotive force. The total voltage that is going to be produced is going to be the electromotive force, epsilon. Okay, this is epsilon symbol. This is the one that represents the electromotive force. What is the EMF? What is it? It is the total energy that is produced, or the total voltage that is produced by the battery. Okay, so the total voltage produced by the battery is epsilon, and then there is going to be some internal resistance, small letter r, which is going to consume some of the energy. And then there is also going to be the external resistance, which is the appliances that you need to power. Okay, so those are going to be consuming the rest of the energy when the small amount has been consumed by the internal resistance R. Okay, so that is what we're going to look at right now. Okay, so what are we saying? We're simply saying here we've got our battery which is producing a total voltage which we called electromotive force epsilon. Okay, and the internal resistance small letter r has consumed some of the energy, and now the rest of the energy is going to be consumed by the external load, which is the external resistance, which we'll call the load. Okay, so the load is the external resistance, that is R. So we've got two here resistors, the small letter r, which is the internal resistance, and then the capital letter R, which is the external resistance, which is the load of the circuit. Okay, so what is the amount of energy that is going to be consumed by the external load? Remember, we said voltage is actually current times resistance. We found this relationship from the from Ohm's law, that said here current is called voltage over current is called voltage over resistance, and we said you can play around with that and you get your voltage as current times resistance. So the external load or the external voltage is going to be current times resistance, which is the external resistance, the capital R. Whereas the internal load or internal voltage is going to be the same current. Remember, we said in this case, this battery is going to be connected in series with the external load. Anyway, so the total here voltage that is going to be consumed is going to be the same current multiplied by the internal resistance. So remember, voltage is IR. For the external, it's going to be current times external resistance. For the internal voltage, it's going to be current times the internal resistance, which is small letter r. Okay, so what is epsilon? Epsilon is the total of these two, internal voltage and external voltage, which is epsilon is going to be V plus IR. We call this IR. Okay, IR, the small letter r. So this is going to be our total voltage produced by the battery, epsilon. All right, so this is what we know about the total voltage that is produced. So there's going to be voltage that takes care or caters for the external load. There's going to be voltage or energy that takes care of the internal load, which is the internal resistance, small letter r. So there are two types of voltage there: the internally consumed and the externally consumed. These two together gives us the total produced energy of voltage, which is the electromotive force, epsilon. Okay, so let's look at how the energy is consumed. So there is we're starting here from the source of the energy. So here, just like previously, we're seeing our current, if you follow that arrow here, moving or flowing from the positive terminal through the resistors and back through the negative terminal. So our current starts from here, which is the negative terminal we're having here, and actually the peak, when the current or the charge leaves the positive terminal, it carries all the energy, which is the epsilon. You can actually see here. Okay, so it moves through the battery. It's still carrying the total energy, epsilon. Then it gets to the internal resistor, where the IR is consumed. Okay, so the voltage is used up here. The IR, the small resistance multiplied by the current, IR, is consumed within the battery, so that when it finally exits the battery, it's no longer carrying the total potential energy, but is now carrying V, which is the current times the external resistance. So that is already, by the time it exits the battery, the IR, or the internally consumed voltage, has been consumed, it's lost already, and then it exits. So when it gets to the resistor, the final or the rest of the voltage here is actually used up. Then it goes to 0, and then the cycle continues. It goes back to get all the energy again. Epsilon goes through the battery. Okay, as it goes through the battery, it means the internal resistance loses some energy there, or some voltage, exits the battery, goes through the external resistor, loses the voltage, and then comes back. So this is how the energy is used, or how the voltage is used within an electrical circuit. So there's positive work done here. What is positive work? As the circuit, the charge is moving through the battery, it gets its positive, it gets charged, it gets positive work, it gets the energy to the maximum voltage, which is the epsilon. Okay, so positive work is done on a unit charge by the battery, transferring an energy equal to the EMF. Okay, the charge does work to overcome the internal resistance here through through the internal resistance, the small r. It's doing work. So by doing work, it's actually losing energy. So it does work to overcome the internal resistance. Okay, and then when it exits the battery here, there is so actually internally the work done there is actually IR, as I said, current times the small resistor. And then when the unit charge leaves the battery, it has energy, less energy than the original EMF. Okay, this is now the total energy that it can use to do work against the external resistance. So that is the V for the external load, which is epsilon minus the internally consumed voltage, epsilon minus I, small letter r. Okay, so after that, then it exits the battery, and then it goes it remains with IR, which is current times the capital letter R, for which is going to use to move through the external load. Okay, so the EMF of the battery is constant, guys. Okay, so how does the battery produce the energy? There is a chemical reaction that is occurring within the battery. So there is a limit, or there is a constant EMF that a battery can produce. Okay, so that's, having known that, okay, we can actually see now that the potential difference across the terminals of the battery will now depend on the current drawn by the load. Why are we saying that? Remember, we said here epsilon, I'm going to put a capital an E anyway because I can't write quickly the epsilon here. This is equal to what? IR, okay? IR minus what? Minus IR. Okay, so as we said, this is going to be constant. The epsilon is going to be constant. When the epsilon is going to be constant, and actually now, okay, and the current is higher, okay, so if the current is higher, we are going to have a smaller resistance. Why? Because these two will always be constant. Epsilon is constant, IR must also be constant. So if the current goes up, the resistance goes down. If the current goes down, then the resistance goes up. Okay, so that is the logic behind this. Okay, so we can actually see that the potential difference across the terminals of the battery is dependent on the current that is drawn by the load. The higher the current, the lower the potential difference, because the EMF is always constant. Okay, so for the same reason, the potential difference only equals the EMF when the current is very small. Remember, here we are simply saying EMF is going to be equal to the IR minus what? Let's go back here. Okay, so here we are. EMF, which is epsilon, is going to be V plus IR. Okay, so if here the current is very small, okay, if the current is very small, V is going to be equal to epsilon. You can actually see here, if the current is very small, V is going to be equal to epsilon. Okay, so which means if you actually measure the voltage of the battery without any external load, you are simply going to find the epsilon. But as you put in the external load, this V is going to go down much lower than the epsilon. Why? Because there is the external load. So at very low currents, the V will actually approach epsilon. Alright, so there is definitely a limit to the current that can be drawn from the battery, and that limit is IC. IC for critical current. This is critical current. Okay, so that is the limit. That is the limit. So let's see the relationship between the critical current and the epsilon. Imagine that you have got a wire with no resistance that you use to connect the terminals of the battery. The circuit is complete. The circuit is complete. Current will flow, and adding any resistance, the circuit will decrease the current. So as we add the resistance, the current will definitely go down. We saw the relationship. Okay, so the current will go down because epsilon is constant, and IR must always match the maximum, which is epsilon. Alright, so the current without any external resistance will be IC, which is the critical current. Remember, if there is no external resistance, V is equal to epsilon. So this is what we are saying. V here is equal to epsilon, yeah, and the V will be the current times the internal resistance. Okay, so 0 is called epsilon minus ICR, which is the current, the critical current multiplied by the internal resistance. Okay, so remember, there is no external resistance. That's why we've got F0 here. So it means current times the internal resistance is equal to epsilon, which is the electromotive force. So current, or critical current, is equal to epsilon over internal resistance. So if you know your internal resistance, and you know the epsilon. The critical current that can be withdrawn from that battery is epsilon over R. So that is the maximum current, which is the critical current of that battery. Alright guys, so there we are. That is the end of this video. All the best.